This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. Hope you had a very good semester break. So your PCBs are still under fabrication, and we hopefully receive in the coming days, and we will update you. So this week the lab, the plan is you will be doing the soldering practice, and you can collect your components. So we have got all the components in a bag so that you can collect it easily. So this year, not a much hassle with the components because we are packing everything in a bag and giving you. Last year, if you check with your previous batch, the distribution of the components was a big issue because we get everything in the lab and then you come and collect it with small bags. And then this time we got the feedback it was difficult, so we packed it in a bag, and so you can collect your bags this week. And then we will update you about the PCB arrival, because I think there was a harvest festival in China. I don't know if you are from China, you know there is a harvest festival. So because of that, none of the companies were working in the last week. But it's good that you are out of China because so you could do some work. See, that is the reason we asked you to submit your PCV before this one, because then you got an excuse. You can celebrate Harvest Festival, so I can't submit my PCV. So that is a genuine reason, we know that. So that is the reason we asked you to submit your PCV before the Harvest Festival. So today we will be discussing about phase locked loops, PLL. Usually people use the abbreviation PLL. So what is a phase locked loop? So before going to study PLL, we should know where we need PLL or what are the applications of PLL. Clock recovery and data recovery, jitter and phase noise rejection. You can multiply, clock multiplication and division. So this is what you do in your DSO. You multiply clock using PLL. You can also do division, but in DSO you are doing multiplication. You can also do frequency demodulation. Then split phase data synchronization and decoding. So these are the main applications of PLL, and in DSO you will be using a PLL for clock multiplication. But then I will also touch upon some of these applications. I think apart from clock multiplication and division, frequency demodulation widely used. Then clock recovery and data recovery, again widely used. Maybe I will touch upon those three applications when we study PLL. So there is a simple experiment that can prove that PLL is required, phase locked loop. So the simple experiment is you are designing a system, and then in your system so when you design a system, you are designing a communication system, say it's an optical communication system. So in the optical communication system, you have got some data. Your data is something like this. So this is 1, 0, 0, 1, and then these are the data, and then you have got something like this. Again 1, 0, 1, 1. So 1, 1, 1, 0, 1. Something like, so you are getting, see, 3 channels, you are getting this data, and then what you do is these channels, maybe this is 100 megabits per second. So this is 100 megabits per second. So these all are parallel channels. So you are getting these 3. Then what you are doing is you are going to convert this into this 3 into 1. So a parallel to serial converter. So then you are converting here, and then here the data rate will be how much? 300 megabit per second. So you are getting the data here, and then that data maybe something like this. You made it serial, something like that, 1, 0, 0, 1, 0, and so on. So here you are getting the data, but when you do a conversion, then you need a clock. Then you will be connecting a clock here, a clock frequency, FCL, because then only you can do a conversion. And then after this, what you do is, usually then you connect to this part will come, maybe a laser driver, and then there is a laser diode, LD, and then maybe there is some optics. And then what happens is your communication, the data will be going like this to some area. So you are getting the data. So this is a transmitter part of a communication, simple laser communication system. Then the transmitter part is fine. So when you receive it here, so here you got an optics, and then this is some distance x, and then you got a photodetector. Then when you have a photodetector, it is detected, then maybe an amplifier, and then what will happen is after amplification you recovered this data, then you are getting the same data here because you amplified it. But the question is then now you have to convert this serial data into parallel. Then the choice is clear. You will buy serial to parallel converter, because here you have used a parallel to a serial converter. Here you will use a serial to parallel converter. But then when you have this type of conversion, then you should get the data here. So this is a x, y, z. So you should get x, y, z. But then problem is when you connect it, then which clock you will use here? You know my question? Because that one is a distance x apart. Maybe it is 10 kilometers, or it is say in one building to building communication, a simple case. So it is some distance apart. Then this clock, maybe you know this clock frequency is FCLK, that is equal to k megahertz, an example. And then can I connect another signal generator here of same frequency? I know the frequency required. Can I connect a signal generator here? So why can't we connect a signal generator there? Because you are generating clock. Why can't you connect it? Yeah, synchronization problem. Because here also the clock you are connecting, then the clock usually here maybe some processor will be there, and then that will be controlling this data, and then this data is coming from somewhere x, y, z. So this clock and this data here is synchronized. When you receive it here in the DSO, your clock and your data are synchronized. Why? Because you got a microcontroller, and then whatever the data is coming, that is synchronized with respect to your clock, the data. But when you receive it, there is a problem. You are getting the data, but then you are triggering with some clock. Then that clock is not synchronized. So then it will not shift it properly. Then the only solution is you have to recover the clock from this data. So that's the reason we use PLL. So that is one of the major applications of PLL. So that is clock recovery and data recovery. So then PLL can recover the clock, and then that clock is synchronized with respect to your data. So that's one of the main applications of PLL. That's the reason this communication is a very good example. Another example is you want to multiply the clock. You have got only 10 megahertz crystal, but then you need a 40 megahertz clock. Then you can use the PLL to multiply. So that's what you are doing in DSO. You are multiplying your clock using PLL. Another application is you want to divide the clock. In some areas you need 40 megahertz, but in some areas you need 5 megahertz. But your crystal is 10 megahertz. So you can multiply, you can divide, you can use PLL. Another application is frequency modulation. You can do frequency demodulation. So after receiving the modulated signal, then you can do the demodulation and recover the signal. So these are the main applications of PLL. So now we will study what is PLL. PLL stands for phase locked loop, and is basically a closed loop frequency control system. So that is the reason it is called a phase locked loop. It's basically a closed loop system. So it is not operating in the open loop, it is operating in the closed loop, which functioning is based on phase sensitive detection of phase difference between input and output signals of the controlled oscillator. See this VCO, voltage controlled oscillator. We will study that one. So basically what it does is the PLL, if you look at the input, it got two inputs. So this is V1, another input is tapping from the output of VCO, or tapping from the output, and then this they do a phase comparator. Here they have got a phase comparator. Then we will study the major working principle of PLL in the coming slides. So PLL contains three main elements. A phase detector, because you need to detect the phase between your signals. So this input signal with respect to the output. A low pass filter, a voltage controlled oscillator, a VCO, we call it as VCO, we will study VCO. These elements are connected with a negative feedback loop. So that's what we do, a negative feedback. So these three blocks, when we connect with a negative feedback, we can make a PLL. So then when you think of PLL, you might think that these all are discrete components. No, they implement in chip, the PLL circuit. So in the chip they will be designing a phase detector and a low pass filter and VCO. So using these three we can make a PLL. And in the PLL, when you give if you connect simply 10 kilohertz square wave, it's not a data, simply a square wave, 10 kilohertz, then PLL output also will be 10 kilohertz. So we will come to that point. So PLL basic block diagrams. So this is a comparator input, phase comparator, not a simple comparator, it is a phase comparator, low pass filter, then voltage controlled oscillator, then this is for comparing. So input is compared with respect to the output from the VCO. So when no signal input is applied, so you just turn on the PLL, then no signal, see here you don't connect any signal, the error voltage, so then there is a error voltage, so this is the error voltage is this voltage minus this voltage. So when you don't have any input here, so your error voltage will be this voltage. So that's the reason this error voltage at the output of the phase comparator is equal to 0. So when you don't have any signal, so you don't have any signal here, then what will happen to the error? Error is this minus this. So when you don't have any signal, then this is the only component present, so you don't have any phase error. So then this error will be 0. The voltage VDT from the low pass filter is also 0, so that when there is no error here, no voltage means though there is no error signal, and then this part also 0, there is no signal here. Then what will happen? When you have 0 to the VCO, then VCO still will give a frequency. So VCO means voltage controlled oscillator, means it will generate some frequency depending upon how much input to voltage you connect here. So if you connect to 0 volt, VCO output will be maybe 1 kilohertz. If you increase 0 volt to 1 volt, VCO output will be 10 kilohertz. So you can increase the frequency by varying the voltage. So that is called voltage controlled oscillator. See, voltage, you are using voltage to control the frequency. So when this is 0 volt, then this still will give some frequency, that is called center frequency. So PLL got a center frequency. Then people will ask, what is the center frequency? The center frequency is nothing, you just turn on the PLL based on your low pass filter, the values used and VCO, then you will be seeing some frequency, it will generate some frequency, and then that is called because then here error equal to 0, here also there is no output of the low pass filter, and then at 0 input voltage the VCO will produce some frequency. So that is called the center frequency, means when you turn on the PLL, you see the center frequency, you will see some frequency of oscillation, that is called center frequency. So when an input signal is applied, then when you connect an input signal to the PLL, the phase comparator compares the phase and frequency of the signal input. So it will compare the phase and frequency of the signal input with the VCO frequency. So VCO frequency is this frequency, means the center frequency. So you already got a center frequency, and when you connect some signal here, it will compare this signal's phase and frequency with respect to this one, and then that will generate an error. When this error is there, then this will give a voltage, and then that voltage will vary this frequency, and then what we'll do is after a couple of cycles quickly it will happen, and this frequency will be locked into this one. So when the input signal is applied to the PLL, the phase comparator compares the phase and frequency of the signal input with the VCO frequency and generates an error voltage. So here there will be an error voltage proportional to the phase and frequency difference of the input and the VCO. So you get an error. This error voltage VET is filtered, so it will be filtered using a low pass filter and applied to the control input of the VCO. So it is a control input of the VCO and signal input frequency. When the input frequency is sufficiently close to the VCO frequency, so when the input frequency is sufficiently close to the VCO frequency, the closed loop nature of the PLL forces the VCO to lock in frequency with the signal input. When the PLL is in lock, the VCO frequency is identical to the signal input except for the finite phase difference. So what it basically does is first it will make synchronized. So your data will be, when you connect a data, what will happen is this is your data you are connecting here. Then when you turn on PLL, then you are having a center frequency. So then what will happen is this signal and then this clock both are not at all synchronized. You know that one, because this is coming and then this signal is coming, then both are not synchronized. Then what will happen is when it is not synchronized, what will happen? One signal will be shifting with respect to another one. So that is called a phase. There is a phase difference. There is also a frequency difference. Then that will generate an error signal. That error signal will come to the input of the low pass filter. This error signal we will not connect directly to the VCO. Why? Because VCO need a kind of a DC voltage. So this error signal might be varying. And then it will put through a low pass filter and make it somewhat smooth. And then we connect to the VCO. Then what will happen is when the VCO input is, the frequency will increase accordingly. See, then this frequency will increase. And then again take the difference. And then this error may be less. And then so on. So after some time what will happen is your data frequency and then this PLL frequency will be matched. That's sort of in a couple of loops. And another advantage is both will be synchronized. So when I breadboarded one phase lock for the first time, I was quite fascinated to see. Initially, when you connect PLL, then I was checking this input signal with respect to this VCO output. So I could see that initially one signal was moving. So I connected channel 1 input signal, then channel 2 VCO output. So VCO output was a clock, and then channel input was data. And then it was moving like with respect to one another. There is nothing. But after some time, what I can see is the signal is coming and then locked like this. It both became synchronized. So that's what PLL does. So when it is synchronized, now if you come back to the optical communication case, then your data will be here. Then you can tap your clock from here. See, both are synchronized, and then frequency also will be useful, means same for the process you want to do, serial to parallel conversion or whatever the process you want to do later in the receiver side. So locked and unlocked states. So PLLs have locked and unlocked state. As I said, when it is locked, then it matched. There is no phase difference. In the locked state, the derivative of the phase difference is 0. Means phase of the input signal minus phase of the output signal that is coming from the VCO output, the derivative is equal to 0. This in turn implies that input frequency equals output frequency. So that's the reason when the derivative equal to 0, we can say that your input frequency and output frequency here both are equal to 0. So that's the reason it is matching the phase, and then it is synchronized, plus the frequency also is same. Then PLL dynamics. As a PLL is a feedback based system, otherwise we won't be able to correct it. It has dynamic behavior which includes factors such as instability. So PLL has instability, setting time, oscillatory behavior. So because of that, if you look at PLL from mathematical point of view or from the transfer characteristics, so we will model it as a second order system because of these problems such as instability, setting time, oscillatory behavior. So one of the questions people might ask is, okay, so I can connect any frequency to the PLL, PLL will lock into it. No, it is not possible. That is only ideal PLL. So when you have PLL based on the settings, they will say that, okay, this PLL center frequency equal to 1 kilohertz. And then you can synchronize maybe 1 kilohertz plus or minus some value. So you can't have an infinite range. So if the center frequency equal to 1 kilohertz, then maybe 900 hertz, you can connect it that range, then it will be okay. Then PLL will adjust. 1K may be adjusted to 900. Because the center frequency, when it is off, there is a center frequency. That center frequency could be 1 kilohertz. Then your data frequency, then you are connecting some input to data, that data frequency might be 5 kilohertz. You know what I meant? Then if the PLL in the real world will not, this 1 kilohertz will not become 5 kilohertz. It can't, match it to that one. So they will say, when you take the data sheet, they will say, what is the range you can connect? So if the center frequency equal to 1 kilohertz, they will say that, okay, this PLL, maybe you can connect 1.5 kilohertz, it is fine. Maybe the 1 kilohertz will adjust to that one. So there is a locking range. You cannot have a big range. And then it is locked, unlocked. Locked means when you see on the oscilloscope, you can see both are kind of coming and then quickly it is locking to each other. Unlocked means again it will be not synchronized. You will see that is unlocked. Again, PLL got overshoot, undershoot, oscillation, dampening factors, all of which affects the locking behavior of PLL. So that's the reason sometimes the locking will be affected by these factors. That's the reason we model PLL as a second order system. Yeah, so in the PLL we will go a bit more in depth, like the first block. So when you take a PLL, the first block is a phase detector. How would you make a phase detector? Because when you study each block in depth, you will understand the working principle a bit more detail. So phase detector, the simplest form of phase detector is a XOR logic gate, XOR. XOR means when both are 0, your output equal to 0. When both are 1, your output equal to 0. But one is 0, one is 1, it is 1. Again, one is 1, another one is 0, it is 1. So we will be having XOR. So here you can see, why do we need a XOR logic gate? Because when this is matching with this one, both the phases are matching, it is 1, 1, so it is 0. You know what I meant? And then when it is both are 0, it is 0. So when this one is 1, this one is 0 means not matching actually. So you should have something error coming. So that's the reason we are using XOR logic gate. Then we will be using a low pass filter. You are well familiar with the low pass filter. These filters are designed to both store the current frequency output state of the PLL as a DC voltage and tailor the PLL's response to change in phase error. In general, the filter is designed to either reject changes in the system input frequency or track changes in the frequency at a defined rate. So I will come to that point. The basic PLL filter topology is simple RC low pass filter. And then, so here, why do we need a low pass filter? That's my question. So these low pass filters are designed to both store the current frequency output state of the PLL and tailor the PLL's response to changes in phase error. Means when you connect to the PLL to the low pass filter, the error is coming. That error voltage you need to smoothen it, and then you have to connect it to the output of the VCO, because VCO need a DC voltage. And then again, your filter, when you have a low pass filter, the output is depending upon the frequency. So that's what it says. Store the current frequency output state of the PLL and tailor the PLL's response to change in the phase error. In general, the filter is designed to either reject changes in the system input frequency or track changes in the frequency. So we will be tracking the changes actually, because there are applications. The PLL low pass filter is designed separately when it is for frequency demodulation or when it is for phase error rejection. There are different applications. So depending upon the application, it will be the design will be slightly different. So what you have to understand is, why do we need a low pass filter is, here the error signal will be varying, but then your VCO, voltage controlled oscillator, needs a somewhat a stable DC type output. So that's what this low pass filter does. Then VCO. So VCO is a voltage controlled oscillator. So when you plot VCO output, so this is output, the frequency versus voltage. So when the voltage is increasing, the frequency will increase. That's what VCO. So omega equal to omega 0 plus K VCO into V control. So when V control equal to 0, omega equal to omega 0. So when you turn on the VCO, it got a frequency omega 0. But when you increase the voltage at the input, then the frequency will increase. So this is a very good representation of VCO. So you can see control voltage 0, 340 megahertz, at 1 volt, 350. See, initially from 1 volt to the frequency is this much, and then frequency will increase towards the right when you increase the voltage. And then, so VCO oscillators. VCOs are generally based upon either harmonic or feedback oscillators, based upon LC type circuitry with sinusoidal output, superior frequency stability and accuracy. Then, but hard to implement on ICs. So when you have VCO, so VCO oscillators, VCOs are generally based upon either harmonic or feedback oscillators. So voltage controlled oscillator means that's an oscillator, but the additional feature is you can vary the frequency not by varying the RC, resistors and capacitors, rather those all are constant, but you are varying the voltage and then getting the frequency, changing the frequency. So you can implement a VCO using a harmonic or feedback oscillators. because feedback or harmonic oscillators, I don't know whether you studied oscillators in your previous subjects. How many of you studied oscillators in your previous subjects? Okay. Yeah, anyway, I'll be teaching you some oscillator sections, because as a system engineer you should be knowing oscillators, and then I will ask you questions, you too, because you studied oscillators. So VCRs are generally based upon either harmonic or feedback oscillators, and then when you are using these two oscillators, the advantage is they are very stable and then accurate. Accurate means stable means the clock is very stable, it will not move, and then accuracy means your frequency will not vary. It is not easy to make an oscillator, because the oscillator will work, but then it can shift it, the frequency. And but then these type is very good, but it is hard to implement on ICs. When you are implementing on ICs, it is difficult. Another one is called relaxation oscillators. More commonly implemented in monolithic IC designs are simple digital circuitry. So relaxation oscillators are very simple to implement, and we can get a high frequency. So these are generally relaxation oscillators are implemented in IC. Just some more information about VCO. Yeah, so this diagram I prepared so that you will get a bit more idea now. So this is V1. So V1 is this square signal, see, and your output. So output of the VCO is this signal. In that case, what will happen is you will get an error, phase error. See, this is a phase error, it will be generated. So this is the error signal. See, now you can see this error signal, this signal you cannot connect to the input of the VCO, because VCO need a DC voltage. So when you connect this into the input of the low pass filter, then the output will be, see, somewhat smoothened, and then this will be connecting to the VCO, and then VCO will be giving another frequency. Then what will happen is this will be, after 2-3 cycles, this difference will be very small. That's what VCO does. So VCO will adjust the increase or decrease the voltage in such a way that your error equal to 0. So that's how it is matching happening. So chip die PLL. So PLL is a hybrid device. Why? Because PLL has both analog and digital components to create the internal filtering and oscillators. The PLL implementation on FPGAs and ASICs, sometimes multiples, takes up a considerable portion of the silicon die due to its loop filter section. So because it got a loop filter, and then you can see the filter is big, and so it is 1.2 mm. See, so basically if you got a 2-3 PLL, your chip will be full, because you need a big space for implementing PLL, good PLL. So means PLL you can get in the chip. Then now again, before going to another application of PLL, then we will study VCO a bit in detail. VCO, voltage controlled oscillator. So voltage controlled oscillator is a part in PLL, but VCO got lots of application, not only in PLL. For example, integrated IF voltage controlled oscillator that can transmit the audio signal from a cell phone to the FM broadcast band. So this type, so what is the use of this one? When the user places a cell phone speaker near the microphone, he or she can listen to the cell phone audio via vehicle's FM radio. Means suppose there is a situation, you are nowadays the car got lots of advanced features. Suppose you got some what I would say, some car from 1980s, the classic cars, and then in that car you don't have any Bluetooth, you don't have any sensors, and then but you are an electronics engineer, then there is a radio, but then you are using mobile, because even though you are using the classic car, you can't get rid of your mobile. But then the system, the requirement is somebody is making a call, then you want to hear on the radio. What you will do? Then what circuit you can make? So that's what. So somebody is making a phone call, then you will put your phone near a microphone. So your phone also, you are not turning on your speaker. Speaker is very bad. Otherwise, you can say that I will turn on my speaker and then go. This one means you don't have a very good speaker in your phone. So again, you bought a classic maybe mobile phone. And so the requirement is when I am driving the car, somebody is making a phone call, then I can just accept the phone and then put it near a microphone that is near the car. So then that microphone will pick up my sound that whoever is talking, and I can hear through the radio. So how can you design it? So that is a design question. So transmit audio signal from a cell phone to the FM radio. So then you can use it. See, so there is a MAX 2606 IC, and IC1 is an integrated intermediate frequency, that is called IF, voltage controlled oscillator with a differential output that supports 70 megahertz to 150 megahertz frequency range, which covers the whole FM radio band. So it is simple. So here is your microphone, and then you can have this 0.1 microfarad AC coupling, and then because this is a microphone, and then the microphone is receiving the signals, means the sound from your mobile phone, and then it is going through this 0.1 microfarad capacitor. Then you have got some resistance to adjust, and then this is the tuned signal. And then so this one is a MAX 2606 is a VCO actually, and then this one also you can connect an antenna, and then these are some inductors. So if you connect like this, what will happen is even you can talk here, and then this will transmit. So you can, it's kind of a simple, maybe a simple radio transmitter. So you can transmit it. How it is possible is when the sound is coming, and this one is generating voltage accordingly, and then that voltage is changing the frequency, and then it's doing the modulation. And so this is with the microphone. Then if you already got the audio signal, if you want to transmit to somewhere, then you don't need a microphone here because you already got the audio signal. Then you can connect it here, BNC connector, you connect it here, and then you can transmit. See, this is a simple setup. Means what is the requirement is you want to convert your audio signal into electrical signal and then transmit. So this is a FM band, so this will transmit in the FM band. So this circuit definitely works. If you are interested, got some time, it is worth trying. So it's really fun. So in the DSO project, you are using PLL. See, when you are transmitting from here, then you got the radio. Then your radio will be picking up the signal, and then you can hear the sound. So that's how it works. But then this is a very good circuit actually. You can try. It's a simple transmitter circuit. For DSO projects, you are using only for multiplication, because you got this S1, S0, 2 pins, and then you have got the crystal oscillator. And in the project, you will be simply using a PLL for clock multiplication and division. The advantage of a PLL IC in this application is the ability to generate multiple stable clocks from only one low frequency clock source. So that's an application of the PLL. When PLL is used in combination with a counter timer like one found in microcontrollers, huge range of frequencies can be generated. So please, in the PLL there will be always 2 pins like S0, S1. Please remember that. So using that one, you can select the multiplication. So clock multiplication and division. So that's what we discussed. So we discussed about clock recovery and data recovery. So now we will study another important application called clock multiplication and division. So clock multiplication, so that is easy to do with the PLL. In the PLL, if you connect 10 megahertz, you will get 10 megahertz out. But if you connect 10 megahertz, and then if you hear divided by 4, if you are putting a divided by 4 counter here, then what you will get is 2.5 megahertz. So here it will become 2.5. When you have 2.5, then what will happen is 10 megahertz minus 2.5 megahertz. So the difference is very big. When the difference is very big, then the error is very big. Low pass filter output, then that will be a big DC voltage, so that VCO you will get 40 megahertz. So that's happening. So this is 40 megahertz, and then this is, after some time what will happen is the error will decrease and then it will be stabilizing. So this will become 40, and then this will become 2.5, and this is 10 megahertz. So then you can generate a 40 megahertz easily from 10 megahertz. So you get to divide it by 4 counter. So clock multiplication division. The division by n in the feedback loop multiplies the output clock by n, which can then be divided by m to make a net multiplier of n by m. So you can have multiplication, then you can have division, something like this. So PLL can be used for multiplication and division. Another application of PLL is frequency demodulation. So what do you mean by frequency demodulation? So when I discussed about VCO application, here you will be doing a frequency modulation, actually FM radio, because based on your signal some sender frequency is modulated with your input signal. Means when nothing is connected, what will happen? This is a VCO, it will be oscillating, and then you are getting some frequency, and then when you have some input signal that is from your sound, then that will be modulating that frequency. So that's the reason you are getting a frequency modulated signal. Then what do you mean by demodulator? So here you are transmitting frequency modulated signal, and in your car the radio is receiving this, and then you can hear the sound, but you don't, in your car you don't have the radio. What will you do? Then you have to design one. So how will you design one? But then you need to design, first you have to demodulate your signal, then you can have a speaker. So how do you do demodulation? Demodulation means from here you got the signal, but then you have to recover the audio signal from that signal, high frequency modulated signal. So far what we did is this one. So you got the audio signal, and that could be from a mobile phone. Then this is your microphone. So this is your audio signal, and then that is going to your VCO. So that's what here, see, this is the VCO, and then this is the antenna. Then you are getting a frequency modulated signal, because VCO got a center frequency, then you are modulating your frequency with the audio signal. So that's the reason here frequency is more, frequency is less here, because there is a voltage is low, this is a falling edge, again leading edge. So that's the reason you get a frequency modulated. So this is FM, frequency modulated signal consists of a 10 kilohertz carrier frequency is modulated by a 400 hertz audio signal. Suppose this is a 400 hertz, and then your carrier is 10 kilohertz. So it's modulated by 400 hertz signal. So that's what is transmitting. So if you got a radio, the radio will pick it up, antenna will pick it up, and then it will demodulate and then amplify and connect to a speaker. But if you don't have a radio, again you can design a demodulator. So how will you design a demodulator? So demodulator means then you can have an antenna, then you can, PLL can be used as a demodulator. Usually how will you do demodulation? Diode, you can use a diode, and you can get the envelope out when you are doing amplitude modulation. So there are different techniques. So PLL can be used for frequency demodulation. How the PLL can be used is, this signal is detected by antenna, then maybe you can do a little bit amplification, and then you can connect it to the PLL input. So when you connect it to the PLL input, what will happen is it is going to the phase detector, because when you connect it, there is already some frequencies existing, the center frequency, and then it will take the difference, you get an error signal, then it is going through a low pass filter. When you are going through the low pass filter, what will happen is all the high frequency components will be gone, and then you get your audio out. And then if you want to get the signal, the clock for further processing, then you got the clock here, 10 kilohertz clock will be available here, then you get your signal here in the PLL. So that is a PLL based FM demodulator. So then you can get your audio, and then you can also recover your carrier here, and then you can use it for further processing. So PLL also can be used for demodulation. So when PLL is used for frequency demodulation, please see that you are taking output from the output of the low pass filter. So that's, because the signal, and then VCO output will be usually a clock frequency. So that's the reason here you will get your audio signal. So PLL basic. So F0 is called the center frequency. So the center frequency is very important when you buy a PLL, because based on your application should be close to the center frequency. As I said, your center frequency is 1 kilohertz, and then your data frequency, you are going to recover the clock. Your data frequency is 50 megahertz. It is not going to work. So PLL got a locking range. So the data sheet will tell you. So PLL applications, again frequency demodulation. So CD4046B, so that's a PLL. In the PLL, here you can connect FM signal input, and then you can design your own low pass filter so that you can have some tunability, and then here you can get the demodulator output actually. Means there are ICs, so you can see PLL and then PLL for frequency demodulation. So in some of your application, maybe as a system engineer, you might encounter you have to do some frequency demodulation. Then you should remember, yeah, PLL can do frequency demodulation. Then you can search PLL for frequency demodulation. Then if your application is in low frequencies, you may see CD4046B. And then when you buy that IC, you don't have much headache, because phase comparator, VCO, low pass filter. So phase comparator is already built in the IC. VCO is already built in the IC. Only low pass filter you can design based on your frequency range. That's a good way, because if the low pass filter is inside the IC, the problem is then the frequency you can't vary much. So this one means you can design your own low pass filter, and then you can tune the VCO for your application. Then you can connect your FM mode signal here, the frequency modulated signal from the previous case, and then you can get the demodulator output. When PLL is locked on the FM signal, the VCO tracks instantaneously the frequency of the signal. See, PLL, the center frequency of VCO is designed to be equal to the carrier frequency, 10 kilohertz. So that's what the center frequency. So that's the reason. So your center frequency is 10 kilohertz, then your carrier frequency also should be 10 kilohertz, or other way around, your carrier frequency is 10 kilohertz, then you will be looking for a PLL close to your carrier frequency. So mostly it is the same is good. Then they will say that PLL was set for a capture range of plus or minus 400 hertz using R3 and C2. See, means you can make a capture range. What do you mean by capture range? If your carrier is so PLL center frequency equal to 10 kilohertz. So PLL center frequency equal to 10 kilohertz means when you don't have any input, you turn on the PLL, and then your center frequency equal to 10 kilohertz. So when you connect a carrier with a 10 kilohertz, that is fine. But if you got a different carrier frequency, if your carrier equal to 1.4 kilohertz, still it is fine. It will work. But if it is above 1.4, it might not lock it. So that is the reason there is a capture range. So you should, your center frequency is 10 kilohertz, then your input must be 10 kilohertz plus or minus 400 hertz, because PLL cannot synchronize or recover the clock or can do demodulation if your input frequency range is far away from the center frequency. So that is called the capture range. See, capture range, they will say that there is a particular range. So clock recovery and data recovery, jitter and phase noise rejection, clock multiplication and division, frequency demodulation, these are the important applications. So some we discussed, some we don't have to discuss, because jitter and phase noise rejection is a very specific application in some communication circuit. So clock recovery and data recovery is very important. Clock multiplication and division is very important. Frequency demodulation is very important. So as I said, the jitter and phase noise rejection is a bit complicated. For that, we should be first studying the communication circuits, and then we have to study the jitter. We will study the jitter. Then what is the problem with the phase noise? Because of the different amplitude, different modulation techniques. So we don't need to study, but we know that jitter and phase also can be rejected using PLL. But clock recovery and data recovery, everybody should be knowing as a system engineer. Why we need PLL? You should know we can use the PLL for clock multiplication and division. We can do frequency demodulation. So why I said the other one is complicated is the following. So this is another application, clock and data recovery circuit. So this is used in the communication, and again you don't have to study, I am just showing you. In the communication, see they are using a PLL here, 4046B, this PLL here. So this PLL will do clock and data recovery. So which I already discussed why clock and data recovery is required. Because when you transmit, you are transmitting the signal, but for that signal you need a clock to further process it. So you need to generate a clock from the data. But then when you actually implement, it will be something like this. In the communication circuit, when you implement something like this, data is transmitted without any additional timing reference in the electronic systems. So you have got a TXRX, you have got a SPI, there are a couple of interfaces. So in some interfaces, you know that there is a clock. You know that one? Let's transmit, there is a clock. So which one got a clock? Anyway, I'll be teaching the communication protocol as an extra lecture, not covered in the final exam, because you should be familiar with that one. So that's the reason when we transmit in some communication protocol, when we transmit some data, we also transmit the clock, because both are synchronized. But when you don't have the synchronization, then we will be using a PLL. In optical communication, a stream of data sent through a single fiber with no accompanying clock, and the receiver is required to process this data synchronously. The clock recovery from the data is essential for processing the data. And then, so this one you don't have to study about this circuit. What I have shown is, well, I have drawn some clock signals if you want to, but then here the summary is what I discussed at the beginning. So you got some data coming, and then you need a clock synchronized with that data for the further processing. So PLL can recover the data. So these are some good references for the PLL if you want to read more. The Circuits and Filters Handbook, the PLL Performance, Simulation and Design is from National Semiconductor. Then Phase Lock Techniques, then Digital Frequency Synthesis, and then yeah, I think these three are maybe a bit more relevant if you are interested, especially the third one is maybe good, Phase Lock Techniques. So there are different types of Phase Lock Techniques. So these are just for your reference in future, not for the exam. So I put always reference at the end of each lecture, because we don't have a textbook for ESD, because this is not based on a textbook. So these references will be useful when you work as a system engineer in future, or a electronics engineer. When it comes phase lock, you can read from these references. So now next, so these are some very good videos. So I would recommend you to go through these videos. And so these videos will give you some idea about the PLL, how it is locking, because that you should be knowing how it is locking. So phase lock loop basics, National PLL design tool. So these are some good videos. And then now my next lecture I will start power supply design, because power supply design is important again for a system engineer. You should know how the power supply works. Most of the time you will be buying a power supply like a regulator, but we should know the power supply. So if you don't know about the power supply, we can make several mistakes like noise filtering. We will not be knowing. For example, you are using a linear regulator, parallel series regulator, parallel regulator, switched mode regulator. So you can buy off the shelf ICs, but then we should know what are the differences. So how it is working, how voltage is stepping down, how voltage is stepping up. So why do you need switching mode power supplies? And then when you are using switching mode power supplies, your efficiency will be high. Why? But then there will be noise when you are using switching mode power supply. So all these things we should be knowing. So that's the reason the power supply design is important for a system engineer. So we will be starting in the next lecture the power supply design. So now we can take maybe 5 minutes break.
Do we have time tomorrow? Because I want to discuss with you about the code. So I read the code in this holiday, and I feel a little bit confused of the Mail Studios code.
No, we will be providing the code anyway, but you wrote your own code.
Pardon?
We will be providing the